I'd like to start by inviting you to take a step into the future with me when one day, maybe not too far from today, we may all decide to chop off our perfectly functioning limbs, replacing them with artificial limbs, providing us with strength, speed, dexterity, agility, and in general, freeing us from the flesh and blood limitations of our own biological body. This is not entirely science fiction. We already have off-the-shelf artificial limbs that in the right hand can provide really high level of hand function and dexterity. On the other side of the spectrum, we see a rise of new technologies that are specifically designed to enhance the functionality of an already fully functioning body. These are motor augmentation technologies that we'll talk about later today. Now, these technologies are, of course, fueled by societal need and are enabled by technological breakthroughs. But I would argue that to make these technologies really successful, we really need to consider the really complex interactions between our bodies, our brain, and cognition, and how they could facilitate safe technological translation. So when we think about the body and the brain, we tend to think about primary sensory and motor cortex, where the body is represented in a map-like fashion with specific body parts represented separately and adjacently. And within it, we have the hand area, which affords both the control, the motor control of the hand, but also sensory processing of information from the hand. Now, when we think about how we can best interface these new technologies with the brain to afford hand function, there's an interest in trying to take advantage of the infrastructure that we already have, that has already been designed through evolution to support our own biological hands, and replace them with the technology that we're interested in. And the idea is that if we can plug into the nerve system that already knows how to handle hands, then the user will be able to control the technologies more swiftly, successfully, smoothly, and in general be better users. We call this vision technological embodiment, and one clear barrier for the realization of technological embodiment is foundational knowledge in neuroscience, where we've known to decades that if you lose one part of the body to amputation, for example, plasticity mechanisms are going to trigger a process of cortical reorganization, where the neighboring representations are going to take over the freed up cortical territory. This creates a clear barrier for technological embodiment, because if your hand area is now your face area, where are you going to stick your artificial body part representation? So from that, it's clear that it's really important for us to understand what kind of resources and infrastructure exists before and after amputation, how it is modulated by changes to the body. And to answer this question, one approach that my lab has been taking is taking advantage of a very ubiquitous phenomena, which is called phantom sensations. People following amputation report that they can still experience the body part that has been lost. These are known for being painful, but they don't have to be. We're merely talking about the sensation that the hand is still there. And let me show you what happens in the brain of amputees when they are moving their phantom hand. So here you see an amputee moving his intact hand in the scanner, and this is just to show you how hand representation normally looks like in the brain. Now we're going to ask him to move his phantom hand, so not much is happening up on the screen because the hand is not there. But if you look at the bottom, you can see that the brain responds to the movement of the phantom hand in a very characteristic way that looks like normal hand representation. This is from our very first study showing that pretty much every amputee we scan can engage or activate the territory of the missing hand just by attempting to move their phantom hands. Sanne Kickert, a former student in my lab, has taken this a step further by trying to understand whether this persistent or preserved representation actually contain typical features of hand representation. And in healthy people, as you see now on the screen, the representation of the hand is characterized by a map of the fingers, so that each of the fingers, thumb, index, middle ring, and pinky, are represented separately and adjacently. Now we're going to see the map of an amputee that had been missing his hand for over 30 years. He doesn't have a hand to move about. Instead, we're asking him to move the fingers of his phantom missing hand. And as you can see with this act, the participant is able to activate a typical representation of his missing hand with individual representation of each and every one of his fingers. Hunter Schoen, a current student at the lab, has taken this a step further by trying to understand whether these persistent finger maps actually store the unique knowledge and experience that individuals have been storing as they were going about their lives. And to address this question, he's been working with a patient with a slowly progressing tumor in her arm. She needs to get an amputation, and here Hunter scans her a couple of days before her amputation, and he's looking at the representation of her healthy hand and her unhealthy hand. So for the healthy hand, you can see a nice, pretty map of the 5 fingers with the fingers represented separately and adjacently. Now, when you look at the fingers of the unhealthy hand, it looks a bit more messy. We can still make up all 5 fingers of the hand, but the map is not as nicely organized as you can see for the healthy hand. And this is probably because the tumor has been eating away at the tissue and the nerve, and it's actually quite difficult for the patient to move her fingers individually. The interesting question for us is what happens to this messy map following amputation? So here are her brain scans 3 and 6 months following amputation, and I hope you can appreciate that at least qualitatively, the representation that we can elicit with her phantom hand looks very similar to what we've seen before for her unhealthy hand. And this tells us that the unique fingerprint of this person's hand is stored in the brain and accessible. So now that I've convinced you that there is infrastructure, hand infrastructure, that is preserved following amputation, the next question for us is to understand then whether we can take advantage, and in what way can we take advantage of this existing representation to recycle it in order to support motor control or representation of an artificial limb. So here we're going to take a little step back from the sensory motor cortex to the back of the brain to the visual cortex, where we and others have shown that also exists selectivity to specific body parts as well as hands. So these regions predominantly respond when you show people pictures of hands and upper limbs more so than other body parts or object categories. So for each individual participant, we would first present images of hands and objects so that we can pinpoint to these hand-loving areas. Then we're going to show them images of prosthetics, artificial limbs. And we're showing here 2 categories of prosthetics. One are the cosmetic prostheses that are specifically designed to mimic the aesthetics of a biological hand. And the second category is functional prostheses, which don't really look like hands at all. They look more like hooks. And the interesting question for us is how does the brain represent these artificial limbs, whether you use them or not? So let's start with control participants. We're using a brain decoding technique here in order to determine how similar the representation of artificial limbs is to that of hands versus tools. And these are linkage trees, so the shorter the branch, the more similar or indistinguishable the representation is in the brain in these visual areas. And as you can see here, for control participants, cosmetic prosthetics, those that look like hands, are represented pretty much like hands. Whereas functional prostheses that don't look like hands are represented very differently from hands and instead are represented more like tools. This is pretty straightforward. What happens in prosthesis users? So here we have a large group of people that are prosthesis users because they're missing a hand for various circumstances. And what you can see here is that the representational structure is quite different for prosthesis users compared to control participants. And specifically what we see here is that both types of prosthetics, the cosmetic and the functional prostheses, are represented very differently from hands. They're also not quite represented like tools. Instead, it seems that the 2 types of prosthesis are represented separately as a new category, meaning the brain takes these hand-selective areas in order to represent artificial limbs in a whole new way, which is distinct from how the brain tends to represent hands. So this is for artificial limbs for substitution. What about augmentation technologies? And here we have a really unique problem. Given a fully occupied body representation in our brain, where are we going to find room for an extra body part that we've never had before? And given that we can integrate a representation of a new body part, how is this going to impact their existing representation of our own biological bodies? And to answer this and similar questions, we are very lucky to be collaborating with the wonderfully talented Dani Claude, who designed the third thumb that you see here on the video. Dani designed her thumb to be used by people that already have full capacity with their hands. And the idea is to allow people to expand their motor repertoire in order to allow them to do more with their already functioning hand. The thumb is controlled by 2 pressure sensors, allowing for 2 degrees of freedom, which we put underneath the toes. With one, you can flex and extend, and with the other, adduct and abduct. So you get pretty much a full range of movement as your biological thumb. Paulina Chialiba, a former student in the lab, was interested in understanding what would happen to our own biological representation of our hands after semi-intensive training to use the third thumb. So she's going to scan participants before and after 5 days of a training kind of boot camp in order to allow people to learn to use the thumb. This is the type of tasks we use in the lab in order to train people to use the thumb. So we ask them to learn to collaborate between the movements of the thumb together with the hand to manipulate objects. In other tasks, the thumb would do one thing, for example, stabilize a cup, while the hand is doing something else. Here, the participant is extracting marbles from the cup. Other tasks are designed specifically to allow people to develop increased dexterity with the thumb, and for that, we're actually occluding the biological hand itself. We've also given the thumb to participants to take home with them for these 5 days and use it as they like. And what we find is for an average of 3 hours a day, people engage and use the thumb in their own daily routine and outside the lab, indicating that at least our participants found some utility for using the thumb. This is my own favorite task. This is a coordination task, so participants are asked to move the thumb to find the tips of each and every one of the biological fingers. I like the task because it requires really full range of the 2 degrees of movement. This is the performance of the participants over the 5 days of training. Notice that even in the very first time when they're just figuring out how to perform the task, they're already scoring some hits, meaning they're already finding the tips of their fingers. So it's a very intuitive design and easy to use, but they do get better with it with days. Before and after the 5 days of training, we repeated a similar task, but this time we've blindfolded the participants. Now, participants were always using vision in order to guide and control the thumb. So this is the first time for them to do something with no vision. And as you can see, they're actually quite good at it. And this is cool because it means that they're actually developing a sense of proprioception of the position of the thumb relative to that of their own biological fingers. If you're wondering how it feels like to have a thumb for 5 days, we were interested in that too. So we were giving participants statements about embodiment, questions like, it seems like the extra thumb belonged to me, or that I am in control of an extra thumb. And we've asked them to state how much they agree or disagree with the statements. And as you can see here, after the 5 days of training, people were more positive or less negative about these statements, indicating that at an experiential level, they really felt like the thumb was becoming a part of them. So, given all that, how would the representation of the participants' own body change after 5 days of this training? So here we're using, again, a brain decoding technique in order to identify the representation of the 5 fingers. So each dot here is one of the fingers: thumb, index, middle ring, and pinky. Right hand is the augmented one. Left one is the one that we haven't augmented. And this is at baseline. And the further the dots are from each other, the more separable or distinct the representation is, the more information we have about each of the fingers relative to the others. And this is in primary motor cortex. Now, following the training, this is what we find. We still see the 5 fingers, and the representational structure is quite similar, but the distances between the fingers for the right hand are very slightly reduced, meaning we have a shrinkage in the representational structure of the hand. I should have said participants are not wearing or using the thumb during the scanner. We're really just probing their biological hand representation. And what this means to us is that there's some plasticity mechanisms in play to change the way our own body is represented that is induced by intensive usage of the thumb. So to summarize, I would say if you're designing for the future body, try to stay close to the body and not too close. There are mechanisms in our nerve system that are specifically designed to integrate sensory information in order to optimize motor learning and improve motor control, and we should take advantage of them as much as we can. But this doesn't mean that in figuring out how our future bodies should look, we should stay very close to the body and mimic the features in the way the body looks and is operated and is functioning. And this is because we do have plasticity mechanisms at play that can change both the way we represent these artificial body parts as well as our own body. More generally, I would say that we should try and, rather than copying the model of hand function, think about how we can abstract the principles that are important for our daily functioning and think about how we can exploit them to new use. And I very much hope to see augmentation, motor augmentation technologies taking this new step into the future. Just a quick shout out to my wonderful lab and the very talented Danny Claude. Thank you.
Hi there. Thank you so much for really introducing us to this. Let me just ask you real quick. You were working with hands right now, but have you already explored also other limbs, or was the hand the one where you said this is the most effective way where we can get a lot of results really quickly?
Hand function is incredibly important in our daily life, and there's so many disorders that impair our hand function that really impact people's ability to work and integrate with the world. So we are interested in hand function as a primary outcome, but to substitute or to augment hand function, we don't necessarily have to think about hands. So there's a range of technologies and a range of additional body parts in nature, such as tentacles or antennas that could potentially be used in order to facilitate hand function in the future. And I hope motor augmentation will take inspiration from those.
We have also a question from the floor. Bionic limbs, how does neurocognitive coordination extend this biomechanic solution?
I'm not sure I understand the question.
It says bionic limbs, how does the neurocognitive coordination extend this biomechanic solution?
Well, I mean, it's a bidirectional relationship. So, you know, we would design code and software in order to best predict what the user is trying to do and come up with solutions for that. But at the same time, brain plasticity mechanism and cognition would both be two important tools in order to try and understand how the software or the machine is trying to implement its solutions and work around them in order to find the best operating procedures.
Now, you mentioned that most of the people that you worked with had a very positive sort of reaction. Are there any patients, anybody that you were working with that said somehow it didn't really work? Are there any people that are not meeting the criteria?
So far, we've only explored with a relative small subset of participants that we were able to work with in the lab. This technology is not commercialized yet. In these early days, people that sign up to take part in the study understand what they're signing up for and have a positive attitude towards it. It is really important to think about, you know, diversity, both cultural but also in body shape and circumstances that might be differently able to integrate the technologies, and this is something we're keeping an eye on.
You were mentioning the phantom sensations, and for some people it's really tough to understand because they are looking for a certain body part that they don't have any longer. So some have really struggling with also depression. Does that actually get away, or basically can you treat this as well by giving them the limb that they can actually use it again? Have you made there any kind of connections?
I would argue that at least today and in the next 20 years, the artificial limbs that we are able to produce are very distinct from biological hands, and I don't think we can fool the brain or the users to think that they are just as what they used to have. So we are a long way from Luke Skywalker arms.
There are also people in the audience who are asking, so of course other sort of scientists are also out there trying maybe something similar. So are you in contact with, for example, Hugh Hare at the MIT and the biomechatronic research?
Yeah, so Hugh has really pioneered the idea that we don't just need to substitute a body part, we can actually use the available technological solution to increase the physical abilities with this body part. So in other words, he was one of the pioneers to blur the boundaries between restoration or substitution technology and augmentation technology, and we're all very much inspired by his work.
What will be the neural and cognitive cost for these kind of technologies that you work with?
I think that's that's the most important question to ask, because there are clear opportunities for cost. For example, if we think about a factory worker in an Apple factory that has to work for 10 hours a day, 6 days a week, if they have to operate an augmentation technology, such as, for example, the third thumb, and then at the end of this workday have to come out and, let's say, drive home, we can clearly predict that their motor control would be potentially a bit more clumsy, or they would need to take some time to adapt to a new situation. So there are potential consequences and costs. Other important scenario to think about is children. They have more plastic brains. We don't know if they will be exposed to these technologies, how the brains would react to that, and now that would impact their ability to operate their own bodies or other technologies. And these are questions that I think are very important to research before these technologies become an everyday reality, which I believe they will be in the near future.
And what do you think makes these technologies unique and different from what we already know, like other tools and substitution devices?
So the augmentation technologies overlap substantially with both tools and substitution technologies, both in the technology that is being developed, but also in the aim to do something different with the body. Where they diverge from these existing solutions is that when we use a tool, we would use our hands in order to control the tool, so that we're substituting one function, which is our current hand function, with whatever the tool is doing. When we're working with motor augmentation technologies, what we try to do is use the augmentation together with our hands without giving up on them. So now we need to figure out how we can collaborate or coordinate between our functioning hand and this additional tool, which also means we need to figure out completely new interfaces of how we control the tools that don't exclude our hand function. And these are really difficult challenges from a neurocognitive perspective, but also from a technical perspective.
Thank you so much, Tamar, for taking the time and really sharing this with us. Thank you so much. We're out of time, but if you have questions, Tamar is still here, so please get in touch with her.